So what is on the screen in front of you is Newton's first law of motion. In the absence of a net external force, an object will not accelerate. Mathematically, what Newton's first law says is this. So if you're not familiar with this notation, this is a Greek sigma, it's a Greek S. The S stands for summation. So sometimes this is called the summation of the forces or sum of the forces, S-U-M, not S-O-M-E, the summation of the forces. Sometimes this is called the net force. Sometimes you'll see it written without the sigma and an F sub net. Either way works for me, but I'm going to stick with this. This is the notation that I prefer. But this is the net force, the summation of the forces. Newton's first law says that this quantity, whatever it is proportional to the acceleration of an object. This is the mathematical symbol for proportionality. This says that if you put a lot of force on an object, it's going to accelerate at a high rate. It says if you put a little bit of force, it's going to accelerate at a lower rate. Now, it's a little bit non-specific. We want to have something better than this. And so what we do when we're faced with the proportionality, what we always do is run some experiments and determine what's called the proportionality constant. It's what determines the actual explicit relationship between the quantities on the right side and the left side of this proportionality. In other words, we take this proportionality, run some experiments, determine some constant multiplier, and turn this into an equation. This is bread and butter physics. This is how we proceed in a lot of things. And if we do that in this case, what we find out is that the net force acting on an object is proportional to the acceleration of that object through the object's mass. The sum of the forces, or summation of the forces, is equal to the mass of an object times its acceleration. So this is more specific. I can say more specifically now, if I put a large amount of force on an object, it will accelerate at a faster rate. And then if I say that if I put a less amount of force on it, or a smaller amount of force, it will accelerate at a lesser rate. What I have to say is that that's true as long as I'm keeping the mass the same. Because now the mass plays a role in how this works. And you know this instinctively, right? If you've ever pushed a couch across a living room, you know this. If the couch is really big and massive, you can put a lot of force on it. It doesn't accelerate very much. But if the couch is really light, you put a lot of force on it and it accelerates quite a bit. You know, in driver's ed, you probably learned that it takes a lot of force to stop a train, which is why you should never try to beat a train. Let me be paternal for a second, right? That's because the train is really massive. And so any acceleration is going to involve a massive amount of force. And the train is so massive that a large amount of force can still probably only produce a small acceleration. So this is basically Newton's first law in mathematical form, and then expanded to determine the explicit relationship between the force and the acceleration. Newton's first law tells us this. This is Newton's second law. This is Newton's second law. It is Newton's first law mathematicized, which is what we always want to do. We in the sciences are in the business of making predictions. We do that by describing the universe around us mathematically. If we do it correctly, the mathematical equations we develop will help us to make predictions. Newton's first law makes general predictions. Newton's second law now mathematically makes specific predictions about what happens to an object of some mass under the impetus of some force. So this is Newton's second law. Now, to be really strict here, what I really need to do is add the vector symbols, because a force is a vector and an acceleration is a vector. And we know that these vectors, at least in this universe, can have up to 3 components. We have an x direction, a y direction, and a z direction that are available to us. One of the things we saw when we studied kinematics was that the great advantage of dealing with vectors is that we can decompose them into elements that lie along our coordinate axes, which enables us to analyze motion in different directions independently. The same thing is going to happen here. So it is possible to write this: the sum of the forces in the x direction is equal to ma sub x. And the sum of the forces in the y direction is equal to ma sub y. And of course, just to be complete, sum of the forces in the z direction is equal to ma sub z. And so we find the same thing we did when we studied kinematics. Doing a two-dimensional Newton's second law problem, or even a three-dimensional, we don't do a lot of those, that's physics too. Well, we might do some, but the reason we don't is because of what I'm trying to say, and I'm stopping myself. To do a two-dimensional Newton's second law problem is the same as doing a one-dimensional problem twice. To do a three-dimensional Newton's second law problem is to do a one-dimensional problem 3 times. So if you can do one dimension, you can do all of this, which is why we typically stick to just 2 dimensions in this course. We'll have to deal with the third dimension a little bit when we start talking about torques, and you'll deal with it a lot when you go to physics 2 and start talking about electricity and magnetism. But basically, if you can handle one dimension, you can handle 2, and if you can handle 2, you can handle 3. There's no difference mathematically as to what goes on. But this is Newton's second law in a nutshell. We'll see some examples as we go on, but that is all for the concept. And it will become more clear as we see more and more examples.